that we are doing. So the main reason why we are celebrating this is like the motto of Women in Cloud Native is to encourage more women to the cloud native ecosystem and to inspire women to achieve their goals and learn things in cloud native ecosystem. So also to excel themselves in the industry. That's what we are trying to do. And this Navratri is kind of a festival which actually resembles the kind of Shakti, and it's a feminine energy of goddess. So that's the reason, linking this festival to the motto of Women in Cloud Native makes really good sense to us, and that's where the idea came up. And Ram has been helping me, in organizing this. So I should always say thank you to Ram Iyengar for this. And yeah, so we have, we are done with, I think, 6 days, and this is our seventh day, and I'm very happy. It's been going really well. And today our speaker is Nimisha, and she has been working as a senior engineer with Confluent. Also, she has a great platform and DevOps side of experience. So I'm happy to hand over to you, Nimisha, right now. So yeah, you can take
Yeah,
over.
thanks so much. And thank you both so much for organizing. I'm sure it was a lot of effort, but yeah.
Thank you.
Um, yeah, so hi everyone. Thanks for joining the talk today. So we're going to be talking about cloud native networking and specifically networking in Kubernetes. And we'll also briefly discuss trends in this space. So we can get started. But I just want to say that it might be a lot of information at once, and if I'm going too fast or if people are not able to follow along anymore, just let me know and just stop me, and I'll slow down or backtrack. So yeah, let's get started. Um, so a little bit about prerequisites of what you should know, at least a little bit about to follow along here is just basics of the networking stack, the TCP/IP stack, how IP addressing and CIDR blocks work. And it helps to know some Kubernetes basics, like what is a pod, what is a node, and how we use YAML to specify these things. And some cloud fundamentals as well, like if you've ever done anything on the cloud, created a VPC and subnets, uh, created a public IP, deployed some workloads on it, that can help as well. So some of the takeaways would be, so how cloud native networking evolved, details of Kubernetes networking, the Kubernetes networking model, internal routing, external routing in Kubernetes, and a bit about networking, plumbing under the hood, so on the Linux level, what happens. And then we'll talk a little bit about the emerging technologies and some CNCF projects. So yeah. A little bit about me. Yeah, I'm a software engineer at Confluent, as Bhavani said. I'm on this Kubernetes platform team, so we help teams within the company deploy and manage their apps on the cloud with Kubernetes. And yeah, we're used to managing networks and clusters at scale. Yeah. So this is section one, cloud native networking. Okay, so in the simplest terms, right, what is a network? A network is just a group of devices that are connected to each other and can share data amongst each other. And these devices usually address each other by something called an IP address. It's like me addressing you by your name. So it can be an IPv4 address or an IPv6 address. These are just protocols. And in each of them, there's a certain number of IPs that you can, have possibly. So in IPv4 is 2 power 32 addresses. IPv6 is much larger space, 2 power 128. Um, so all devices that are connected to the internet have a publicly routable IP address. So many IP blocks are actually reserved for various purposes. For example, there are these private ranges. Those are ranges that are not routable on the public internet. So this range is actually reused across many organizations. Um, each organization can have thousands or even millions of devices or hosts having private IP addresses, and these would ultimately, when trying to reach the internet, get translated to a public IP address. Um, Yeah, and this is actually how it works even in your home. If you have a router at home, all your devices like your phone, your tablet, your laptop are actually using private IP addresses. And then your router is converting um, all of those when they're trying to reach the internet to one particular public IP address. And this is called network address translation. And this is how, many organizations around the world can reuse this private space without any worry about clashing or overlaps. Okay, and then there are a couple of other reserved addresses like the loopback address, and that's for communication between devices on the same local link, and the broadcast address. So how did cloud native networking evolve? So what makes networks cloud native? So um, essentially, it's just networks for applications running in cloud environments. But the main difference between networks of the past and cloud native networks is that cloud native networks are very dynamic. Things are always being built up and toned down. So, for example, Kubernetes, pods are very ephemeral. Pods are constantly getting created, getting destroyed. So these networks need to be really scalable and resilient. In the past, things were more static and manual, and today things are more dynamic and distributed. We used to do monolithic architectures a lot before, but now we do microservices more. We used to use VMs, um, but now we mostly use containers. It's like more or less a standard across, the industry. And then we also transition from physical networks to virtual networks and software-defined networking. So all of these things kind of led to the cloud native era. So this is an example of a cloud native cloud network. This is a VPC from AWS. So this shows what it looks like in a given cloud region. So it's a regional service, first of all. You would provision a virtual private network and assign it a single broad IP CIDR range. So this one. And then this CIDR range would typically be broken down into multiple subnets having some slice of that range. So maybe by three. So, 1/3 of the IPs go to subnet one, subnet two, subnet three. And usually subnets are per availability zone. And then ultimately you would deploy some VM instances into these subnets so that each instance gets its own IP address from within that subnet. So in Kubernetes terms, this would be the nodes in your cluster. So your node gets its IP address from the VPC that way. And if you notice, this is also in the private space. But VPCs don't necessarily have to be in the private space. It's just a best practice. Otherwise, it would be very expensive. Um, Yeah, and of course, there are many other cloud services that cloud networking services that cloud providers offer. So there's load balancers, gateways, CDNs, ways to connect between two VPCs, DNS servers, and a lot more. So let's talk a little bit about networking in Kubernetes, just internally, so within the cluster. And we'll start with building blocks. So we're all probably familiar with some of these building blocks, but let's do a quick recap. Okay, so a container is a portable package of an application binary plus its dependencies. Portable as in it can run on any kind of node, any kind of hardware without any changes. A pod is basically one or more containers bundled together. A node is essentially an abstraction over a compute instance, and a cluster is a grouping of all these resources. And most of these constructs are actually logical. So, a container or a pod, for example, doesn't mean anything outside the world of Kubernetes. It's just a logical way of bundling things together. Okay, so yeah, about Kubernetes, the core idea of Kubernetes is to be a pluggable system. It's kind of like a fabric that allows hooking into various plugins and vendors to fulfill a standard set of functions. So, for example, when you create a pod, a YAML definition is sent to the API server. It's persisted in the etcd database, and then the scheduler assigns a node to that pod. Okay, but after that, the the kubelet is the kubelet is an agent that runs on every node. That is a Kubernetes thing. And it's the kubelet that makes the pod available on the node. So it hooks into interfaces such as the CRI, CNI, and CSI, and to set up the pod environment. Since Kubernetes is built to be very flexible, modular, and vendor neutral, each interface may have different implementations available. And some of those examples are shown here. So all these vendors provide some functionality to fulfill, let's say, the CSI interface, or these provide the CNI interface. So what are these, right? So the CRI is basically responsible for container lifecycle management on the node. So it's responsible for pulling images, creating, starting, stopping, and deleting containers. And underneath, it uses Linux C groups to allocate CPU and memory for a particular container. That's how this is actually, that's what's going on under the hood. And then the CNI, which is probably the main component for our discussion today, is what attaches that container to the network. It assigns an IP address from a pool of IP addresses to the pod, and it sets up the routing and interfaces so that the pod becomes routable from within the cluster. So the CNI's job is just to mm, uh, make sure that a pod can be reachable from anywhere within the cluster. The CNI uses Linux constructs, many of them, such as network namespaces, to divide amongst resources, virtual Ethernet interfaces called VETH pairs, and then it uses IP tables for adding the routing and firewall roles, and bridges to set up networking for containers between nodes. So these are all kind of low-level constructs of Linux, but Kubernetes uses these. So yeah, the CSI is similar. It handles the storage needs of the pod, such as provisioning persistent volumes, attaching and mounting volumes to the pod, and so on. So let's talk about how routing works within the cluster. So when two or more containers reside on the same pod, the containers actually share the Linux network namespace and routing table. So because of the shared network namespace, containers in the same pod can actually communicate through localhost and port numbers. So they share the same IP essentially. Each container in the pod should have a unique communication port to avoid port conflicts, as in only one port can be used by one container. So like, this container is listening on, let's say port, 443. This one is listening on port 80, but they are actually communicating over the loopback address. So there's also this other thing, side note, there's a hidden container called the pause container, whose only job is to hold the network namespace for a pod. So every time you create a pod, Kubernetes is actually creating this hidden container called the pause container, which creates the shared resources for all the containers in a pod. You may have seen this pod sandbox not created error sometimes. That's basically the the pause container trying to do the network reservation right before the pod starts up. So what about pod to pod communication, but on the same node? So first of all, why do we even have IPs per pod? That would be a lot of IPs, right? And these things keep coming up and down. It's a lot of work to manage them. So before the Kubernetes model was developed, let's say when multiple applications were running on the same computer or the same host, all those applications had to have separate ports exposed. So like I said about port conflicts, right? One application is listening on port 1, not 1, but 80. Another one is listening on 81. Another one is listening on 82. If they can't overlap. But with a pod having its own IP, all apps within that pod can actually reuse the same port and not worry about the complexity of port mapping, even when there are multiple pods deployed on the same node. So it's like you're separating it logically so that as an application developer, I don't have to worry, oh, what port did that person use? I have to use a different one. You can all use port 80, for example, if you want, and it'll just work. even though those pods may be deployed on the same host. So it helps decouple pods from the hosts on which they run. So for the routing, right, every pod has a virtual Ethernet connection. Think of it like a cable represented by the ETH0 network interface connected to the node's host network. So this is where the pod to host connection is set up. This is called a VETH pair, and it's a pair because there's two interfaces. One is on the pod side, and the other one is on the node side. And they are actually they just come in pairs. So when a pod sends a request to another pod, the request goes out through the pod's ETH0 interface, which tunnels to the node side of the VETH pair that I just mentioned, and then via this bridge that connects to other pods in the cluster. And this network bridge, represented here by this CBR0, resides on the node. And the job of the bridge is just to connect all the pods within a node. So yeah, this pod is trying to request 10.0.0.2. It goes out to the node. The bridge interface connects it to the other pod and has some routing information. And then that's how the request reaches the pod. So what about pods on different nodes? You may think this works the same way, but actually no. The bridge, CBR0 bridge alone cannot resolve the request. So the routing process for pods between nodes actually depends on the networking infrastructure implementation. So it can vary. Sometimes, most popularly, I'm just going to talk about two versions, so tunneling and native routing. So in tunneling, right, an overlay network is created using packet encapsulation protocols such as VXLAN, Geneve, IPsec, and WireGuard. Um, so overlay tunnels abstract the underlying network infrastructure and make it easier to create a unified network across nodes. Um, but the disadvantage of using tunneling is that it takes up space in the packet and adds some necessary overlay headers. So that's some extra overhead. So in your packet, you can send less information essentially. And then the other model is the cloud native networking model, where it's essentially the underlying network infrastructure's responsibility to ensure that each pod is routable from any other node. Um, so each node in the Kubernetes cluster, in this case, will be aware of IP addresses of all the pods on all other nodes. And this is usually advertised by protocols such as Border Gateway Protocol and so on. So this depends on, again, the cloud provider implementation of the network. So the advantage with this one is it takes away the overhead of tunneling that we just discussed. But it's actually just a trade-off of isolation versus performance. So tunneling gives you more isolation. This one gives you more performance. And then there are other routing modes as well. There's direct server return, BGP peering, lightweight tunneling, etc. We're not really going to cover that. But yeah, essentially, it looks similar. The request goes out of the pod, goes to the node side. The node will have a routing table. It knows how to reach all the other nodes. It goes to the second node, and then it reaches the pod inside that node. So there's 4 steps happening. Okay, so network policies, and why am I even talking about this? So as I mentioned, right, in the Kubernetes networking model, by default, all pods can talk to every other pod, even across nodes, to make the routing very simple. It's called a flat network. And sometimes this is not so desirable. For example, let's say a company wants to create a cluster, but they want a separation between, let's say, the front end team and the back end team, or the business ops team and some other team. So they might use the concept of network namespaces to separate things, but the pods would still be routable. Like a pod from the front end team could still reach some other team, the business ops team, for example. So the concept of network policies becomes very important. These are basically just rules, like think of it like a firewall for Kubernetes that controls how pods can communicate with each other. And they allow you to specify which pods are allowed to send or receive traffics from receive traffic to or from other pods, or even external addresses based on labels and namespaces. So you can say something like, okay, this client green can reach test service, but client red cannot reach test service. So it'll deny that connection, but allow this one. And that can be really important for basically network isolation. Um, yeah. So Kubernetes has its own implementation of network policies based on labels and label selectors. But actually, modern CNIs today offer very complex DNS-aware policy enforcement mechanisms, such as Cilium's network policy capabilities shown here. So you can use very complex ways of, filtering traffic, even based on, let's say, if the DNS name, which is like, I'm trying to reach yahoo.com, that is allowed. But if I'm trying to reach google.com, that will be denied, for example. Anyway, as a bonus, I just want to share this talk. It's a talk by Tim Hawkin. It's considered, so he's considered to be the original implementer of the K8S networking model. And he talks about the history and decision making while establishing this. Yeah, if you don't get to scan it now, don't worry. I think the recording will be made available at some point. But yeah, that's something for later. Yeah, a lot of words on this one, but let's talk a little bit about where the IPs come from. Like you might be thinking, okay, what are these pod IPs and stuff like that? So when you create a Kubernetes cluster at creation time, these are actually input arguments. So you usually have to specify a pod network CIDR and a service CIDR. So pod CIDR is basically IP addresses that are assigned to pods from that range. And then for services, it's the other way. So virtual IP addresses assigned to Kubernetes services from this range. So can different clusters use the same CIDR range? Yeah, because usually the CIDR is from private address space, which is again a best practice. It doesn't have to be, but it's more or less the default. So yeah, everyone, like you have two Kubernetes clusters, you can specify the same pod CIDR range for all of them. Of course, an exception would be maybe, let's say, a multi-cluster setup. So ideally, that should have distinct non-overlapping IP ranges to avoid collision. Yeah. So can this be different from the VPC CIDR or a portion of it? So either. It depends on how the network is designed, and different clouds do this differently. It's very common for the VPC CIDR to provide node IPs, whereas pod and service CIDRs are usually separate virtual address spaces that are managed by Kubernetes. One note again, pod IPs are ephemeral, right? So IP addresses assigned to a pod may change as a pod gets recreated. A pod right now may have one IP address. When I delete it and recreate it, it will have a completely different one. And but they're all assigned from a certain pool, which you've input to the at creation time. So now we understand how pods can talk to each other inside the cluster. But let's say now you have a deployment with 3 replicas, and you for fault tolerance you want 3 replicas, and a client trying to reach this app. Do you think the client would remember each pod's IP? Like, oh, I want to reach this one or that one or that one. Probably not, right? And what if the pod is recreated? The IP changes. So does the client have to update its list then? Um, so here is where services enter the picture. Services are designed to solve exactly this problem. A service essentially provides a persistent virtual IP along with a convenient DNS name, so that no matter what the pod IPs are as they come and go, the cluster IP is going to be stable. And it'll have a stable IP, DNS, and port. The DNS name is usually of the format, service name dot namespace dot service dot cluster dot local, something like that. So that if clients connect to this service, the requests are then forwarded to the backend pods. So it's kind of like a load balancer. Uh, excuse me. A service recognizes what backends it should route to using label selectors matching labels on the pods. So of course, it can't also keep track of all the IPs directly, but it let's say this pod has a label app A version 1, app A version 1, app A version 1. So this service has this selector for app A and version 1, and will route requests only to those pods. So all nodes actually know magically how to translate this stuff. So all nodes have the necessary rules to translate the service virtual IP to the IPs of the backend pods. And usually this is, by default, the original implementation is done with Linux IP table rules, which are essentially rules on every node that specify where a packet should be routed. So the rule will have something, a format such as, it'll look at the source IP, destination IP, and the protocol. And for this source, for this destination, and this protocol, route the packet here or there, whatever. So that's how, like, it just magically works because every node has a copy of these rules. The default service type is a cluster IP service. So cluster IP service is going to provide communication capabilities only within the cluster, not outside the cluster. So yeah, this is what I was talking about, where the service has a DNS name, and then it has IP table rules which route to the pods. Okay, so you might be thinking now, how are the correct IP tables magically added to every node? And how does a node keep up with what should be routed where, especially as pods keep coming and going? This is the function of kubeproxy. So if you've seen in a Kubernetes cluster, kubeproxy runs as a daemon set inside the cluster. It runs on each node. It manages network rules as services and pods are created and destroyed. So it keeps a watch on the Kubernetes API server to keep an updated list of all services and backend pods and their IPs. So as you can imagine, this can be a very heavy operation because it always has to, and if there's a lot of churn, it has to do a lot of work to manage those lists. It handles service discovery and load balancing. And even the implementation of kubeproxy itself can vary. So originally, the implementation was IP with IP tables. And then there's another version called IPVS, which is more efficient, but more complex than IP tables. But I don't think it's caught on that much. Most people still use IP tables. There's also a third legacy implementation, but we won't talk about that now. That was like in the initial days of Kubernetes. So a caution about IP tables. Like I said, these rules can be very complex, and every node ends up with hundreds of complex rules, sometimes more. And these rules have to be processed sequentially. That's just how it works. So this is really not that scalable on very large clusters, let's say with 1,000 nodes, which has very high churn, like, pods keep coming and going every hour. So as these rules are processed, it actually increases the latency of the routing So yeah, it kind of becomes a bottleneck sometimes. And also this IP tables only provide basic load balancing. So either round robin or random. And it has high potential for conflicts with other components modifying IP tables. So, for a lot of reasons, you should be careful with this. And it's very hard to debug these. Yeah. So the last piece that brings Kubernetes networking within a cluster together is this thing called the kubedns service. So it's basically a DNS server that comes out of the box with Kubernetes. You don't have to do anything special to deploy it. So Kubernetes, you might start up a pod and try to hit a service and everything magically works, right? The magic is basically that Kubernetes configures each pod in the etc/resolve.conf, if you've ever seen that file, to use the Kubernetes kubedns service as the DNS server to resolve service or pod FQDNs to an IP. So essentially, if you look at the diagram, so this front end pod is saying, okay, I want to reach the backend service. It goes to core DNS, and then core DNS returns an IP, and then the front end pod uses that IP and tries to reach the whatever. It's a service IP. So it reaches the service, and then the service forwards that finally to the backend. So the core DNS component itself is deployed as a deployment It has a Kubernetes cluster IP service with 2 default backend pods. And often this service can be a single point of failure. So a lot of production incidents happen because, let's say, core DNS was not available, or something went wrong with it. It was not behaving as expected. There's this whole link called K8s AF, which is basically failure stories about like how things can go wrong in Kubernetes clusters, and you'll find DNS mentioned on many of them. Um, yeah, okay, this is a separate thing. A headless service is also a different concept. It's basically when you specify a service's cluster IP to be none, and when you try to get the resolution for that service, for example, here, right, it's the core DNS service is returning the service IP, but for a headless service, it will return the IPs of every backend pod. So that's useful in some cases. It's good to know. So, okay, we've talked about internal networking, but we haven't talked about networking externally outside Kubernetes. So we'll touch on that a little bit. Like, how do you expose your apps to the outside world? So we talked about services, but there are actually 3 types of services. One is the cluster IP service, which is the default, which we already talked about, and it's only for internal use. And the 2 types of services to expose apps externally are node port and load balancer. So I found these really cool diagrams that make it kind of simple to explain. In a node port service, a request coming in on any node's external IP gets translated to a port from a port on the node to a pod listening on that port. So your traffic would reach any node on some port, and that port would correspond to some service that's listening on that port, and the service would forward the thing to the pod, the packet to the pod. Yeah. So and then okay, the other version is the load balancer service. Uh, so basically, in this case, it kind of builds on top of the node port service type, but it actually provisions a physical load balancer on the cloud. So there's only one public IP exposed to the world, but ultimately it works the same way. Here I said that you can go through any node, so sometimes there can be multiple hops happening, but here there's only one IP that you can go through, so it's a single hop usually. Yeah, so one thing is the node port service is generally not recommended for production use because it limits, one service per port of the node, and it's mostly used for experimentation. The cons of the load balancer type service, though, is that it can get expensive because, as I said, load balancer services provision a physical load balancer on the cloud provider and assign a public IP to it. So all those things can add up sometimes. Okay, so what is an ingress? You may have heard this term as well. So essentially, it's like a layer on top of services. It is something that provides a single point of entry into the cluster, and then it acts like a reverse proxy for HTTP and HTTPS traffic. So it basically routes, so one point of entry, but it routes to different services based on the HTTP domain name. So for example, this domain might route to that service, this one will go to service 2, and anything else will go to service 3. And then these ingress pieces can provide multiple additional features. So they can provide load balancing, SSL termination, etc. It depends on the vendor. A lot of vendors provide this. You may think this, because it's a single point of entry, it can be a single point of failure. But usually these are, vendors will provide a highly available ingress controller solution for this. So it's usually not a problem. This is like another thing, which is a newer Kubernetes API. It's similar to Ingress, but it provides separation of responsibilities between network infra and actual routing. And it takes this role-based approach. So it has these Kubernetes resources, these are again abstractions. So an infra provider will just create some of the pieces, but the application developer can specify how they want the routing to work. So the separation is there because of that. Another thing, it supports multiple protocols and complex routing rules. It's very good for multi-tenancy. So multiple independent gateways can be used, and it provides good network isolation. And the main thing I think is that, like I said, for the ingress, it depends on the vendor how that ingress is implemented, but Gateway API is meant to be vendor agnostic. So regardless of which vendor you use, is going to be a standardized API. It's part of Kubernetes. Cool. That's all I had for external routing. I'll just briefly discuss like just one thing about networking at scale, which is what kind of things would you be observing? Um, so in terms of traffic, you would observe the inbound, outbound latency and packet loss from nodes. That would be crucial to measure. Another thing would be pod-to-pod connectivity. So there are applications for this. For example, Goldpinger, which is just an application that spins up a pod, pings every other, it's a daemon set. So it spins up a pod on a node, pings every other pod within the cluster and reports how the pod-to-pod connectivity is. It can be a little inefficient though. Um, yeah, and then on the control plane side, you would monitor the Kube API server latency. Oftentimes people use managed Kubernetes service, so they're not controlling, they're not managing the control plane, but you can still monitor the latency and HTTP errors you get from the control plane. Sometimes requests are also throttled, so it's good to measure that. And then about DNS, I also mentioned it can be an SPOF. So it's important to measure DNS latency and resolution failures. And for load balancers and ingress, this is a cloud provider side thing, but you would monitor the data path availability. Load balancers generally come with health checks. So that's something to always ensure is, working in 100%. And SNAT port usage, that's another thing. Yeah, it's kind of nuanced. Apart from that, you would measure within the cluster any TCP failed transmissions or retransmissions or dropped packets. And then from a troubleshooting perspective, I wanted to talk about a few tools that we use, but then I thought that would be too much for this presentation. So instead, there's a link. This is a really cool website. It's called Wizard Zines by Julia Evans. So basically, it's like a bunch of comics that illustrate how to use Linux tools such as TCP dump or Netcat or whatever to actually investigate stuff. So it's written in comic form and it's like really easy to digest. So I really like that one. Yeah, moving on. So other networking technologies. So sorry, before that, does anyone have any questions about from anything we learned so far?
It seems to be, very much in-depth explanation, Nimisha, actually. So, yeah, if you
Yeah.
have any other questions, from folks who joined, please feel free to ask.
I do have one. So, yeah, first
Yeah.
of all, very insightful session. My question is more specific to, let's say, the security policies that, let's say, enterprises have. There can be
Mhm.
policies like FedRAMP, or there can be policies related to GDPR. So, how does one take into account such security protocol while keeping the network constructs in mind, especially when it is cloud native?
Um, I mean, so you could still use, so most vendors will provide FedRAMP compliant images and FedRAMP compliant products. And then you can just use those. So, for example, we actually do use Cilium, for example, to enforce network policies in FedRAMP environments. So, yeah, I think that's kind of, does that answer your question? Or were you looking for something
Yeah,
specific?
yeah, yeah. That answers my question.
Okay.
Thank you.
Um, yeah, and I apologize if it was too much information overload. It can be a complex topic, so there's usually a lot to cover. But yeah, I'm open to questions anytime. This is kind of the last section of the talk. So Yeah, let's get into it if there's
Yeah,
no other questions.
thanks. Thank you, Nimisha.
Yeah.
I think
Okay.
we have one question from Tulasi. Tulasi, are you looking to ask any question?
Yeah, yes. So thank you, Nimisha, for this extensive um, talk on networking. This is everybody's scary area, I would say. Um, and yeah, thanks a lot for this detailed information. I just had a question on this headless service. I
Mhm.
heard about it, and I, you know, um, but not very sure of the use cases. So I was reading the documentation parallelly, but I didn't really get where can it be of use. So
Yeah.
do you have something in mind, a quick use case?
Sure. Yeah. So for example, it's basically used for discovery, for let's say you have a identity. So you have a stateful set, and you have some identity associated with your pods. In that case, a headless service will be useful because let's say a component needs to configure something per pod, and you have pod 1, pod 2, pod 3. It's useful to get the IPs of each pod and then do something per pod. That's one use case I can think of. But in any case where you need to discover all the possible backends, that's like the purpose of headless service. Um, yeah. Does that help answer your question?
Oh, sorry. Yeah. Yeah.
Okay, cool.
I think in a way I can look it up later on. Thank you so much.
Okay.
Cool. Thank you. I think you can go ahead with this topic, Nimisha. Thank you.
Yeah, sure. Just this is like other technologies which are kind of relevant on in the networking space. So service mesh will come up a lot, and I know there's a dedicated talk for this in 2 days, so you can definitely attend that. But basically, in a large organization, let's say where you deploy many microservices applications in a cluster, and they're all implemented in various different languages. You have a Go application, a Python application. Earlier, every application had to implement common functionality. So service to service encryption, TLS, monitoring, tracing. And this is how the service mesh came to be, to bundle all of these S2S communication aspects into what is called a service mesh. A service can just do its thing and not worry about some of these things that the proxy can take care of. And essentially, these are implemented like sidecars to the application pod. At least I think that may be changing now, but that's how it is originally implemented. And Istio is an example of a service mesh which uses Envoy proxies as its proxy layer. So it basically, yeah, forms a mesh within the cluster. It provides uniformity amongst applications, provides some observability and security as well. With TLS. So, okay, that's all about that. And then the other one is, yeah, one of my favorite topics to talk about. And this could be easily its own talk. So, eBPF it stands for Extended Berkeley Packet Filter. It was originally developed it's like a customizable toolkit for the Linux kernel that lets you run safe and small programs directly inside the kernel. So it's like heard this analogy in some of these talks that it's the world before eBPF is like HTML web pages, but after eBPF is like JavaScript for web pages. So how JavaScript allows you to run at the user end dynamically a lot of different functionality, eBPF kind of accelerates networking that much. So it allows you to run these small kernel programs which allow you to observe, monitor, or even modify the behavior of applications or networks without changing the kernel code. So you don't have to, develop a new Linux patch and send it to the Linux repo and then wait for a few months to get it backported. you can now control a little bit of what happens inside the kernel with just eBPF. So it provides high performance and flexibility. And you might be thinking, is this safe? Like, can I just run whatever I want in the kernel? Of course, that's a huge concern. So the safety is guaranteed by this program called the eBPF verifier. And as I understand it, this verifier is still in development. So, I mean, of course, it's there's a version of it that's out there, but people are always trying to improve the verifier and make it safer. So, why eBPF works with requirements of cloud native development is because, especially for routing. So remember how we talked about IP tables and their limitations, like IP tables can be, can explode, and there's so many IP tables to process, it can be a bottleneck. So eBPF kind of takes away all of that, because the number of sequentially processed rules, scalability issues, and all that IP tables has, eBPF can do much more efficiently. Yeah, for example, one thing that you can do with eBPF routing is you don't have to process everything sequentially. There are BPF maps that are inside the kernel that can be much faster to look up routes. So there are many projects that use eBPF for routing, most notable of which is Cilium. So it is a CNI implementation that implements all the network functions of a CNI using eBPF. So it can do a lot more too. We briefly mentioned policies earlier. So it also has a service mesh implementation. It provides encryption and everything. So I have one more link, and yeah, sorry for all the QR codes, but this is a really cool talk by Daniel Borkman. It's a little bit old, but it talks about how BPF as a revolutionary technology for the container landscape. So it really talks about what the vision for eBPF is and how it can change things a lot. So IP tables actually are a 25 or 30-year-old concept that, I mean, I would say they're kind of getting outdated at this point. But yeah, there are other CNCF projects that also use eBPF. So Tigera projects, Calico uses eBPF for container networking, I think. Yeah. Another one is multi-cluster networking. So this is a quickly maturing space. It's multi-cluster. A Kubernetes cluster is restricted to one region, first of all, and sometimes can be considered a failure domain in itself. Because let's say a cluster goes down for any reason. Let's say the DNS goes down and nothing in the cluster can communicate anymore. Having a multi-cluster setup can provide fault tolerance. So better fault tolerance, better resource distribution, and sometimes there are requirements for data residency or latency. So let's say someone mentioned FedRAMP. So let's say for FedRAMP, this cluster has to be in this region and the workload has to be running there. So you can move stuff around and ensure it's running in the right place. So it's a way of deploying apps across Kubernetes clusters, ensuring that there is seamless scaling, connectivity, and coordination between them. So of course, there's a lot of challenges with multi-cluster. It sounds cool in concept, but Kubernetes was built with only one cluster in mind, so it was not built for multi-cluster. So there's a lot of challenges like cross-cluster communication. That's the biggest one. Identifying services across clusters. So let's say I have a service I want to route to two backend pods. One is in cluster A, one is in cluster B. Solving that problem. Synchronizing state between clusters. And let's say you already have clusters running and you want to connect them. So how can it be compatible? The network parameters that you use to create the cluster, are they compatible with each other? For example, the pod IPs cannot overlap. The IP CIDR cannot overlap. So I put this table here. We're not going to discuss in detail, but I just wanted to portray a point, which is that there are so many projects that are coming up in this space. And there's this cool article that kind of does this analysis in terms of architecture, etc. All these fields, how these projects differ from each other. So yeah, that's a cool space to watch out for. So yeah, go ahead. Does anyone have a question?
So there is one thing, like for specific questions about FedRAMP and GDPR, I encourage asking in tag security Slack channel. Okay. So this is like okay. We don't have any question at this moment, Nimisha. I think you can go ahead. Sorry.
Okay. Yeah, another area is edge computing. You may have been hearing this a lot too, and there's a lot of open source projects in this space. You can check out this LF Edge landscape, this Linux Foundation Edge landscape that they've created. So some of the differences in cloud native versus edge native. So sorry, backing up a little bit, edge devices are basically those that uh, are not in the main frame, like the main networking connection. Sorry, I'm losing the words, but basically they're deployed at the edge of the network. It's like a common architecture pattern is to place additional computing devices at the edge of the network so that things can be processed um, close to edge devices, close to, let's say, your smart home device or whatever. Um, the difference between cloud native and edge native networking is basically apps in cloud native definitely can have a reliable high speed network with lots of capabilities. But in edge networking, you basically have to account for a lot of variation. So your networking speeds can change. Some devices may have excellent connection, some devices may not. And the protocols can differ a lot too. So there's Zigbee protocol and so on. There's a lot of non-IP protocol networks to deal with. That's kind of the main differences. The challenges are that IoT devices are resource constrained. They usually have a limited compute capacity and bandwidth. And then you have to, like I said, deal with various speeds and protocols. And another characteristic of edge networks is generation. They generate a large quantity of real-time data. So how do you process all this data efficiently, and how do you make this easier? So people have deployed edge devices as nodes inside a Kubernetes cluster, and a lot of other creative things. So yeah, there's a ton of projects that do this, but I don't know details about it. Yeah, okay. That's all I had to say on that topic. So I think last one. So everyone's talking about AI, of course. So how does AI fit into the networking thing? So on the hardware side, there's a lot of advancements, I would say, like smart NICs, for example, are basically network interface cards that um, do have the capacity to do some processing for networks, so that they take away some of the overhead from CPUs. Um, so this is used in data centers, all of these things. InfiniBand is a technology for very high speed data transfer, low latency networking technology from NVIDIA, extremely high data transfer rates. This is an open source network operating system for switches and routers that was developed at Microsoft, Sonic. So all of these things are good for the hardware side, but for the software side of things, everything we just talked about. So advancements in CNIs, advancements in service meshes, advancements in edge computing even, they all kind of fit into making things more efficient for AI workloads. Um, so I have a question in the chat. So for the latency thing, is edge better than cloud? I would say no, because on the cloud, you have a guaranteed SLA for latency. But for the edge, you're dealing with more uncertainty. You don't know what devices are, on what kind of networks and so on, and how many hops there are to reach that device across the network and things like that. Um, yeah, that's more of a general answer, but I think it would also depend on the use case. Okay, yeah, so that was networks for AI workloads, but what about AI for networks? So definitely there's a lot in scope here. Like AI can help with capacity planning and cloud cost management, so intelligent algorithms for detecting anomalies and troubleshooting, and optimizing bandwidth allocation. So, analyzing trends, predicting, and foreseeing how traffic would be distributed, and also for security. Yeah, this is still a developing space. So all of these concepts that we just talked about, they are still kind of maturing. Some of them are already uh, mature, So, okay, that brings us to our conclusion. Yeah, so how do you get involved? Sorry, this is the last QR code, but it basically goes to this website, plottributor.dev. We'll talk about it in a minute. There's a bunch of special interest groups as a part of Kubernetes. So if you just look it up, you'll find it very easily, I'm sure. For example, there's special interest group for networking, SIG network, SIG multi-cluster. There's a few more as well. And then in CNCF, which is Cloud Native Computing Foundation, there are tags. This was confusing to me. I was like, okay, what's the difference between these? They're essentially similar. Tag is Technical Advisory Group, and even they are organized by function. So there's a tag network, tag security, tag runtime, etc. So yeah, they all have their own Slack workspaces or channels, and they all have their own weekly meetings or bi-weekly meetings. And there's a lot of projects going on in all of them. So if you want to get involved, you should join the Kubernetes Slack channel and the CNCF Slack channel. If there's a way to share the links later, we'll do that. And then, yeah, just try to hang out there and try to see what you can do. And of course, the best way is to start contributing to projects in your free time if you do have time. There's this website, clottributor.dev. It basically links to like all the open issues across all CNCF projects. And you can sort by, you can filter for good first issues, new issues. You can sort by area, you can sort by difficulty level, and so on. So it's a cool way to get started. But yeah. Yeah, that's pretty much all I had. Thank you all so much for attending. I can take questions as well. So yeah, I see one more in the chat. How is it to troubleshoot cloud native networks? Yeah, as someone already said, right, there are a lot of moving parts. So it is definitely hard. Like ultimately, anything in a distributed system is hard to debug. Yeah. So for example, I, I'm not sure if I can recall the details perfectly, but there was one incident I was involved in where an external load balancer on the cloud was failing its health checks, and that's because the thing that is responsible for answering the health check on the node is the kube proxy, and the kube proxy was failing because it was trying to, I told you kube proxy tries to update IP table rules, right? There was another application deployed in the cluster that was also modifying IP table rules. And that every time there's a modification, it's basically, you can't have concurrent writes. So that application was holding a lock on the IP tables rules. So the kube proxy could not update it. And so the connection just broke. Without the rules, there's no way the node will know what to route where. So any packets coming in through the load balancer hitting the node would not get to their destination. That was very complex to debug because it's like, if you have a cluster with 20 applications deployed, you're trying to figure out which application is trying to do what. And yeah, there's a lot of stuff that can, there's a lot of tools that can help here. Yeah.
Yeah. Thank you, Nimisha. Yeah, any other questions? Yeah. I mean, like, so I would say, like, you you mentioned a lot of things in this 1 hour session, so it's very helpful for people to learn about networking. I would say it's a great session, Nimisha. Thank you so much.
Yeah, thank you so much for attending. Yeah. Thanks, everyone. Enjoy the rest of the talks.
Yeah,
Yeah.
thank you so much.
Abhishek,
And I've shared my thanks in a LinkedIn post, so that will be
Oh,
available on
oh,
on.
thank you so much.
thank you so much, Abhishek.
Thank you so much.
Thank you everyone for joining us. We'll be back tomorrow at 8 p.m. Join for that session as well. Like, yeah.
And great to see you, Ram, after a long while. Right. Thank you.
Thank you. Bye.
Yeah, thanks guys for organizing. I'm gonna
Thank you.
drop off too.
Yeah. Bye.
Bye.